Hey there, it's Shannon Math Myers, and today we are looking at section 15.3 from the calculus text by Larsons and Edwards, and we're covering conservative vector fields and independence of path. Woohoo! All right, so our goals are for you to be able to understand and use the fundamental theorem of line integrals, understand the concept of independence of path, and then understand the concept of conservation of energy. So let's warm it on up by showing that the value of the line integral over the smooth curve of the vector field f dot dr is the same for each of these parametric representations of C. Okay, so let's do it. So for part A, we have x at t is beautiful t, and so x prime at t is 1, y at t is the square root of t, and so y prime at t is going to be 1 over 2 root t. Cool so far? Awesome. All right, so if you recall, we need a few things. We need our vector field evaluated at x at t, y at t, and that will be, let's see, x squared plus y squared times I. So we'll have t squared plus root t squared times I, and then minus x times j, so minus t times j. And where am I getting this? Because y at t was root t, and we were squaring it, and then x at t was t. We're squaring that one. All right, and whoa, wasn't what I wanted to do. Okay, and so that, of course, will equal to t squared plus t times I minus t times j. And let's see what we have. R prime at t well, we found the components of it. R prime at t is going to be x prime at t times I, so 1 times I, and then plus 1 y prime at t times j, so 1 over 2 root t times j. Groovy so far? Okie dokie. Now what do we need to do? We need to find the dot product. So the dot product is going to be of the vector field and r prime at t is going to be, let's see, well, t squared plus t times 1 is just going to be t squared. So let's put this into the form of our integral now. So we'll have the integral from 0 to 4 of f dot dr is going to be equal to the integral from, well, I'll keep it in general, the integral over the smooth curve of f dot dr is going to be the integral from 0 to 4 of, so the dot product t squared plus t times 1 is t squared plus t. And then we will have negative t times 1 over 2 root t, which will be minus 1/2 root t dt. Cool so far? All right, so this will be equal to t cubed over 3 plus t squared over 2 minus 1/3 t to the 3 halves, the 2's divide out, and that's going to be from t is 0 to t is 4. So notice that the lower limit, everything will zero out. So this will give us what? 64 cubed minus 16 over 2 is 8. And then the square root of 4 is 2. 2 cubed is 8. So we'll have minus 8/3. And let's see, that in turn gives us, let's see, 64 minus 8 is going to be 56/3. And then plus 24, getting a common denominator. So that gives us 80/3. Awesome. And that was for part A. Now, part B has us do it using a different parameterization. So, let's check it out. So for part B, let's see, we have x at w, right? This time we have a w parameter, is w squared. So x prime at w is equal to 2w. Y at w is w. And then y prime at w is 1. And I think you see where we're going with this. This might end up being a little easier for, to evaluate. So F, our vector field at x at w, y at w, will end up being equal to, we'll have x squared plus y squared. I'm going to go a little faster this time. So w to the 4th plus w squared times I. And then minus x times j. So minus w squared times j. So again, all we did is evaluated it, x at w and y at w in the vector field F over here. Cool, cool? All right, so now, here we go. Our prime at w is going to be 2wi plus 1j. And so our integral over c of f dot dr is going to be the integral from 0 to 2, and we need to find the dot product. So we're doing w to the 4th plus w squared times 2w. So I'm going to distribute that out. So we will have 2w to the 5th plus 2w cubed minus, and then w squared times 1 is w squared, and that will be with respect to integrated with respect to w. And so that's going to be, let's see, w to the 6th over 3 plus w to the 4th over 2 minus w cubed over 3, and that's going from w is 0 to w is 2. And so 2 to the 6, I think that gives us 64 over 3, plus 16 over 2 is 8, and then minus 8 cubed, and as you can see, that's the same as what we had there, so that will definitely yield 80 thirds. Groovy? All right, so what did that teach us? It taught us that basically, you know, you can set the parameter, right? So as long as you adjust your interval for t, or whatever your parameter you choose to use, you'll be good. All right. Personally, I think the purple one was a little easier to evaluate, but neither one of them were bad. All right, let's do it. Let's go to the fundamental theorem of line integrals. So let C be a piecewise smooth curve lying in an open region R and given by R at t equals x at t times I plus y at t times j, where t is between a and b inclusive. If the vector field f at x and y is equal to mi plus nj is conservative in R, and m and n are continuous in R, then it turns out that the integral on that piecewise smooth curve of f dot dr, make sure I did, yes I did, okay, f dot dr is equal to the integral over the piecewise smooth curve C of del f dot dr, which happens to be equivalent to f evaluated at x at b, y at b, minus f evaluated at x at a, y at a. So this should look somewhat familiar, a little more complicated than the fundamental theorem of algebra, but that's okay because it's the fundamental theorem of line integrals. And this f that we're talking about is a potential function of the vector field f. So that means that f at x and y, the vector field f at x and y, is equal to del f at x and del at f at x and y. Okay, so example 1. Find the value, sorry, it's on different pages. Find the value of the line integral over the piecewise smooth curve C of f dot dr. So, let's see. I'll give us lots of room to work at least. So here we go. Well, we might as well identify what all we have. Do you see that m, from here I can see that m is equal to 1 because that's the coefficient of I, n is equal to z, and p is equal to y. Cool so far? So we want to make sure it's conservative. So, you know, since we have a little bit of, well, I'll just do it below here. Okay, so to check to see if it's conservative, right? Let's do it. So, the first partial of m with respect to y is equal to 0. The first partial of m with respect to z is equal to 0. The first partial of n with respect to x is equal to 0. The first partial of n with respect to z is equal to 1. The first partial of p with respect to x is equal to 0. And the first partial of p with respect to y is equal to 1. So let's see. We need to check, does dp, so dp, the first partial of p with respect to y, does that equal to the first partial of n with respect to z? Yep, they both equal 1. So check. The first partial of p with respect to x, does that equal the first partial of m with respect to z? I believe they were both 0, so yes, that works out. And then finally, the first partial of n with respect to x, is that equal to the first partial of m with respect to y? And I believe both of those were 0. Yep. So that means that f is conservative because of all of that. Right? Okay. Well, whoops. Conservative. Sorry. Conservative. Because of all of that. And since f is conservative, that means, woohoo, we get to find our potential function. So that we did the check for whether f was conservative. Now let's go ahead and find our potential function. All right. So the integral of m with respect to x is equal to the integral of 1 with respect to x. So that's going to give us x plus some function in y and z. Our integral of n with respect to y is equal to the integral z with respect to y, which is y times z plus some function of x and z. And our integral of p with respect to z is equal to the integral of y with respect to z, which gives us, again, yz plus some function, oops, sorry, this one should have been h, some function k of x and y. So notice that you've got, these are the same, right? And so since they are the same, we can say that g of y and z is going to equal to yz, right? And we can say that k of x and y will just equal to some k, some constant k. And so therefore a potential function is f at x, y, and z is equal to x plus y times z plus some k. Groovy? So let's go back. We found our potential function, right? Let's go back to this groovy theorem. So both of our curves are piecewise smooth curves, right? And they're both given in terms of, you know, t, x at t and y at t and z at t. And we determined that our vector field was conservative, right? And our m and our n, by the way, this extends, this extends to space. Extends to space. So you also have a z at t, like in the problem we're working on, and a p for the vector field. So so basically, we don't have to do all the work that we did before. We just use that end result, our potential function evaluated at the limits of integration. All right. So let's check it out. Found our potential function, right? And so now if we take a look at part A, right, our x at t is equal to cosine at t, and so now x at 0, right, is equal to cosine 0, which is 1. Y at t is equal to sine at t. Y at 0 is 0. Well, cosine 0, or sine 0, which is 0. Oh, sorry, and I forgot. X at pi is going to be cosine at pi, which is -1. Sine at pi, or y at pi, will be sine at pi, which is also 0. And then z at t was t squared. And so z at 0 will be 0 squared, which is 0. And z at pi will be pi squared. Cool, cool? So, in order to, we're going to use the since this meets all the requirements, right? Do you see m, n, and p? They're all continuous, right? Which was one of the in the real numbers. So, and then which was one of the requirements, and then we had to have a conservative vector field, and then we had to find the potential function. But once we did all that, it becomes a little easier, because the integral over that piecewise smooth curve of f dot dr turns out to be equal to the potential function evaluated at x of b, y of b, y at b, z at b, minus the potential function evaluated at x at a, y at a, z at a. And we found those. So in our case, our b is pi. So we're evaluating our potential function f at x at pi, y at pi, z at pi, minus f at x at 0, y at 0, z at 0. Okay, so this is what we will have. We will have we found x at pi to be -1, right? So basically this ends up being f at -1, 0, and pi squared. Or no, sorry, we got to do the b's first, right? So, oh yeah, that was it. -1, 0, and pi squared, minus our function, our potential function f, evaluated at 1, 0, 0. And I just got these because that is what x at pi was, right? X at pi. And then y at pi was here. And z at pi was pi squared, right? And so that's going to be, well, right here is our potential function, right? And so x plus yz plus k evaluated from negative 1, 0, sorry, 1, 0, 0 is the lower limit, negative 1, 0, pi squared is the upper limit of integration. And so that's going to end up being, I'm just plugging them in. So x is negative 1 plus 0 times pi squared plus k is going to give us negative 1 plus k. And then minus, so 1, 0, 0 would end up being 1 plus k. So that gives us negative 2. Pretty cool, huh? All right. And you know what? My format's kind of crappy here. Let's do a little arrow. Equals negative 2. Good so far? All right. So now let's do part B. We'll do part B in a different color. So in part B, we use the same potential function. We're just doing a different curve. So for part B, x at t is equal to, I'll go a little faster, 1 minus 2t. And this interval is going from 0 to 1. So x at 0 is 1 minus 2 times 0, which is 1. And x at 1 is going to be 1 minus 2, which is negative 1. Y at t is pi 0, right? There is no y at t. So y, it's always 0 no matter what. And so that means that y at 0 is 0 and y at 1 is 0. Z at t will be equal to pi squared times t. And so z at 0 will be pi squared times 0, which is 0. And z at 1 will be pi squared. So f at, actually we'll do our line integral. So our line integral over this curve here, f dot dr, is going to equal to f at, again, x at b, y at b, z at b, minus f at x at a, y at a, z at a. That's going to equal to, so that x at b, so that would be x at 1, so that would be f at negative 1, y at b is 0, and z at 1 was pi squared, and then minus the lower limit, x at 0 was 1, y at 0 was 1, and z at 0 was, or y at 0 was 0, and z at 0 was 0, so 1, 0, 0. So see, this obviously it's the same thing. So one, they're just different ways to represent, to parameterize the curve. Pretty groovy, huh? So basically minus f at that. And we did this below, remember? This is where we were here, right? So we're clearly going to end up, getting the same thing. So, so that's going to end up being negative 2. Cool, cool? All right, so independence of path and conservative vector fields. If f is continuous on an open connected region, then the line integral over the piecewise smooth curve C, f dot dr is independent of path if and only if f is conservative. So it goes the other way as well. If f is conservative, then the line integral is independent of path. Okay? All right, so here's some equivalent conditions. Let the vector field f at x, y, and z equal to m times I plus n times j plus p times k have continuous first partial derivatives in an open connected region R. And let C be a piecewise smooth curve in R. The following conditions are equivalent. F is conservative. That is, F equals del f for some function f. All right? The line integral over the piecewise continuous, or I'm sorry, the piecewise smooth curve f dot dr is independent of path. And the line integral over the piecewise smooth curve of f dot dr equals to 0 for every closed curve C in R. Cool, cool? All right, so let's take a look. Evaluate the line integral using the fundamental theorem of line integrals. Well, let's check out this theorem, right? So what's our m? Do you see that m is equal to 2 times x plus y, and that has continuous first partials, right, in this smooth curve C, and n equal to, same thing, right, 2 times x plus y, so it's going to have continuous partial derivatives in an open connected region R. And C is given as a smooth curve, and from negative 2, 2 to 4, 3, right, so that's the R. So all we have to do is check to see if f is conservative. So the first partial of m with respect to y is equal to, well, you'd have 2x plus 2y, and we're treating the x as constant, so that would just be 2. And that, it turns out, is also equal to the first partial of n with respect to x. So f is conservative. So we've met all of these conditions, conservative, so we can use the fundamental theorem of calculus, right? So let's check it out. So our integral of m dx, because we do need to find our potential function, right, is going to be equal to the integral of 2 times x plus y with respect to x, which is 2 times x squared over 2 plus xy plus some function of y. And our integral of n dx, dy, similarly, will be equal to 2 times the integral of x plus y with respect to y, 2 times xy plus y squared over 2 plus some h of x. And why don't we simplify those? So that would end up being equal to x squared plus 2xy plus some g of y. And the second one would be equal to xy, 2xy, plus y squared plus some h of x. Well, do you see that the g of y would end up being y squared, what we got in that second one, and the h of x would be the x squared from that first one. And so that means that our potential function would be x squared plus 2xy, because they both have 2xy, plus y squared is our potential function of x and y. Cool, cool? Well, what is that? F of x and y, if you want to make it easier, that's the quantity x plus y squared. And we have this path here, negative 2, 2 to 4, 3. So our line integral f dot dr is going to equal to f at 4, 3 minus f at negative 2, 2. Which is x plus y, the quantity squared, evaluated at from negative 2, 2 to 4, 3, which gives us 7 squared, which is 49, minus negative 2 plus 2 is 0, 49 minus 0, so we would get 49. Pretty groovy, huh? All right, so if we, meet all of the requirements, then we can use this groovy fundamental theorem of line integrals. But remember, so, the catch is that sometimes you need to get your, this here was, this right here, right, was our f at x and y, right? So we had to get our potential function. All right, so example 4, evaluate the line integral using the fundamental theorem of line integrals. All right, so here we go. Let's just double check, make sure we got everything good to go. So we have m is equal to 2x over x squared plus y squared squared. And n is equal to 2y over the same denominator. Whoa. So dn with respect to x would be, let's see, negative 6. Actually, it'd be more than that, huh? Because it's to the negative 2. So you'd have negative 4 times 2. So I think it'd be negative 8. xy over x squared plus y squared cubed. And is that equal to dm, the first partial of m with respect to y? So look at it there. You'd end up, for using your chain rule, you'd have a 2y, you'd have a negative 2 from the power rule, so you'd get negative 8xy over x squared plus y squared, the quantity cubed. So we're good. So f is conservative. Now if you examine m and n, they have continuous partials unless x and y are both 0. Then they'd be indeterminate, right? So basically, what's our path? We're going from a circle centered at 4, 5, clockwise from 7, 5 to 1, 5. So basically, we're not we're never going to deal with 0, 0. So we're good. So on our, on our path here, M and N are continuous, so we're cool. All right. So here we go. Let's see what we've got going on. Well, actually, we already have M and N, right? So let's do it. Well, we have to find our potential function, right? So the first part was checking conditions. Now we're doing potential function. And let's see what we get. So the integral of M with respect to x would be equal to, so actually I have everything I need to integrate, right? Because I'll have the integral of 2x times x squared plus y squared to the negative 2 dx. And that, I need a 2x dx in order to integrate, so I'm good. So I will end up getting increased by 1. We'll have negative 1 over x squared plus y squared plus some function of y. And the integral of n dy will be the integral of 2y times x squared plus y squared to the negative 2 dy, which similarly will be negative 1 over x squared plus y squared plus some h of x. So why don't we let g of y equal to h of x equal to some k, some constant, because we didn't end up with any functions alone in x or functions alone in y. So that means our function in x and y will end up being negative 1 over x squared plus y squared plus k. Groovy? Okay, so our line integral, it's in, I'll write it the form it's in. It's, do you see it's in m dx plus n dy, which actually the other one was in as well. And so that's going to equal to, we found our function of x and y, so that's going to be negative 1 over x squared plus y squared. Do you see the k would 0 out, so we don't need that constant? And that's going to be evaluated. So we were going clockwise from 7, 5 to 1, 5. So we will have 7, 5 is the lower, 1, 5 is the upper. So that will be negative, let's see, 1 squared is 1 plus 5 squared, so negative 1 over 26 minus a negative is plus, and then we'll have 49 plus 25 is 1 over 74, and that ends up giving us negative, let's see, we're all done. Cool, cool. All right, so there you have it. Next time we'll be doing Green's theorem. Awesome. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, tell your friends and please subscribe. Bye.